Alright, this is example 2 of finding the area of a segment shaded in the black here. And we have 6 segments in this case, so we are supposed to find the area of each segment. We have a regular hexagon inscribed in a circle, and this regular hexagon has the size of 3 centimeters, so I label all of them in the red right there. And of course, the area of a segment is still going to be the difference between the area of a sector and the area of a triangle. So how do we do that? Well, for the area of a sector, we know that the area of a sector is what? Well, let's see, area of a segment equal a subsector minus a subtriangle. Now, in this case, I'm going to go ahead and use the version, the degree version of the area of a sector. Minus 1/2 times base times height of a triangle. But we don't know the radius, we don't know the base of a triangle, we don't know the height of a triangle. So the first thing we want to do before we can even figure out all of those 3 things is that we have to figure out the degree of the central angle theta. So that's when we will go back to the figure, recognize the fact that regular hexagon is a regular hexagon. Well, of course, that's why it's regular. But to figure out the degree of the central angle, we start from one spot, and then we go all the way around. Well, if we go all the way around, it's 360 degrees total. But because this is a regular hexagon, we know that the degree of each of these 6 central angles is going to be the same. And that degree can be found by taking the total degree, which is 360, and divided by the amount of central angles that we have. So we got 6 central angles. So 360 degrees divided by 6 central angles is going to give us 60 degrees for each of these 6 central angles. And of course, these black lines right here that connect the center of the circle to each of the vertices of the regular hexagon is called the radius. Using the alternate interior angles theorem, if this angle right here is 60 degrees, then of course this one has to be 60 as well. If this is 60 and this is 60, then within this triangle, the leftover right here has to be 60 as well. And of course, using the two same reasoning, the alternate interior angles theorem and the triangle angle sum theorem, we know that all of the degrees is going to be 60, just like that. And this one right here as well. So with all, this one right here. Now we have to figure out the radius, the base of triangle, and the height of triangle. And we only need to take one of these triangle to figure out the radius, the base, and the height. Well, we know the base is going to be 3 centimeters, so we're good right there. So we can just find the radius of the circle and the height of a triangle. So I'm going to go ahead and pick the bottom triangle. I mean, it's the easiest one for me to see. And I'm going to create the apothem, which is the green dashed line right here. And remember that the apothem is the distance that connects the center of the circle and one of the sides of the regular hexagon. And the apothem and that side intersect each other perpendicularly. Because they intersect each other perpendicularly, there's going to be the right angle right there, by definition of perpendicular intersection. And this green dashed line right here is going to be the height of this triangle. So how do we figure out the apothem? Well, considering the bottom triangle here, we can pick either the left half or the right half, and then we use the 30, 60, 90 triangle property, and then we just crank it out. So I'm going to go ahead and consider the right half of this bottom triangle. Let's draw it out right here. So that's the apothem from the bottom triangle. This is the hypotenuse of the bottom triangle, aka the radius of the circle as well. And this is half of the side of the regular hexagon. Now we know that by this figure here, by this bottom triangle here, the apothem bisect this central angle. So this central angle is 60 degrees, and it gets bisected. This left half is going to be 30, and this right half is also 30. And because we are picking the right half, we know that this right here is 30 degrees. This is the right angle that we drew earlier. If this is 30, this is 90, this has to be 60 by the triangle angle sum theorem. Now, by the 30, 60, 90 triangle property, opposite to 30 degrees is a short leg denoted by the letter X. Opposite to 60 degrees is the long leg denoted by the formula, the short leg times square root of 3. Opposite to 90 degrees is the hypotenuse, aka the radius of the circle, denoted by the formula 2 times the short leg. However, because we know the base of the entire bottom triangle here is 3 centimeters, and since we are only selecting the right half of this triangle, we know that this red part right here has to be 3 centimeters divided by 2, because remember that is half of the base of the entire triangle. Well, if x is 3/2, then we know that the long leg here, aka the apothem, aka the height of the entire bottom triangle, is going to be 3/2 times square root of 3. So this is the height of the triangle. Also, since x is 3/2 and the hypotenuse, which is also the radius of the circle, is 2 times x, well, that's going to give us 2 times 3/2, which is just going to be 3. And this is the radius. And this is the height. Again, with the radius now known, the height now known, and the base of each triangle now known, which is 3 centimeters, just plug them all in using the area of a segment formula. So the area of a segment is going to be theta over 360, which is 60 degrees over 360, because remember that theta is the central angle, times pi times the radius square, but the radius is 3, so we got 3 square, minus 1/2 times the base, but the base is 3 centimeters as given, so times 3, times the height, which is 3/2 times square root of 3, like that. Well, this is just going to be a matter of simplification in algebra. So 60 over 360 is going to give us 1/6 pi times 9. 3 squared is 9. Bring down to minus 1/2. Let's see, 3. Actually, not bring down to minus 1/2. I'm going to multiply everything else. 1 times 3 times 3 times square root of 3 is going to give us 9 square root of 3. The denominators multiplied together is going to give us 4. So this is what? 9 pi over 6 minus 9 times square root of 3 over 4. Well, let's simplify. Well, 9 pi over 6 is going to be 3 pi over 2. And 9 times square root of 3 over 4 cannot be simplified, so we keep it the same. But if you want to find a common denominator, the smaller denominator is a factor of the larger one. So we can convert this 2 into the 4 by multiplying it by 2 and multiplying numerator by 2. We have 6 pi minus 9 times square root of 3 over the common denominator 4. And this is going to be the formula. So, I mean, not the formula, the answer. So this is centimeter square. Yes. So the area of each segment is 6 pi minus 9 times square root. 6 pi minus 9 times square root of 3 over 4 centimeters square. But that's only one segment. That's only one of these segments. But since we have all 6 of them, then the total area of all 6 segments is going to be the area of all 6 segments is going to be the amount of segments, which is 6, multiplied by the area or the value of the area of each of them, which is 6 pi minus 9 times square root of 3 over 4. Well, let's see. Simplifying it a little more. 2 is the greatest common factor that goes into 4 and 6. So 4 divided by 2 is 2. 6 divided by 2 is 3. And then we distribute the 3 into each term of the numerator. So we got 3 times 6, which is 18 pi, minus 3 times negative 9. Square root of 3 is going to be negative 27 times square root of 3 divided by 2 centimeters square. So this is the total area of all 6 segments.